Yeah, last time we looked at exact n squared time max flow algorithm, and there is like a one core algorithmic component where which is trying to find its flow. It does the following, right? Like it's like short flow algorithm where you have a graph, let's say capacitated, weighted, doesn't really matter too much. Have some sort and sink, have some parameter d and epsilon, but the point is that it tries to return a flow for this sort and sink such that it's near maximum. The size of the flow is close to maximum, where what do I mean here? Like it's big as f star, where f star is the maximum flow for this sort and sink. It's a maximum flow among all that are short. Okay. Just compare, like f star is like a flow that is like half average length at most d, average length in W at most d. Okay, and then your flow will be as big as f star. Okay, and the running time should look something like this. And in our previous class, this thing, like our epsilon is just some constant, and this term is like something like n log n, and d is gonna be something like n over 5, and so this thing just gives you n square. Like if you remember, like we run this flow algorithm on top of the shortcut graph, right? And why do we run on top of shortcut graph? Because we know that on shortcut graph, kind of the target flow that we try to compete with is it has like the average length of n, right? That's the point of shortcut. You shortcut it so that even like the target flow that you want to compete with now is short. Okay. And if you know that f star have short length, then this subroutine will just give you f that is like as big as f star. Okay, and I just kind of skipped this in class, and today I want to tell you how to do it. So yeah, like we saw the version of this when W is the unit weight. Okay, but like in this version, if you look back at lecture 22, we solved this version when W is just unit. And the idea there is like put the weight of all forward edges to be 1, the backward edges to be 0, and then run just basic push Relabel and it works. Now I kind of don't know the simple argument like that in the weighted case. Like when W is general and we want this kind of running time. So I just gonna tell you how today. Okay, and like how to do this actually is a great exercise to really like for your understanding for push Relabel, and actually it will be in your homework. So what we will do is actually like just the starting point. So what we're gonna do actually is kind of simplified version. It's gonna be still for general weight W. The W is still general, but the capacity is unit. To extend it to general capacity, usually it's just simple. Just use the link cut tree, the thing that I kind of mentioned some time ago. Okay. But the true relaxation here is that I will just show you that how to get flow F. That is not so big, just a constant approximation. Okay, but like it's a good exercise. Like once you see this, how to extend it to get 1 plus 1 minus epsilon approximation, I think it's a good exercise for you to really like do some to do it yourself. Okay, so let's look at the algorithm. Okay, the algorithm is gonna be like push relabel as we expect, but it's gonna be the version that I call it Relabel-Aggressive. So let's see. Okay. Let's focus. Let's not focus on this parameter for now. For now, look at this push relabel algorithm. You have a graph. You have some parameter like maximum height, h. You have the weight function and slack, the slack function for each edge. Okay, like the weight function is like it's just a weight that you assign to both forward and backward edges to some number, and you have slack for this thing too. Okay. Right, and we just gonna kind of start initialize the algorithm in the usual way. You initialize with zero label and empty floor, and we just gonna maintain approximately tight edges. Okay? Use approx tight edge data structure with weight W prime and slack delta. Okay? I hope you recall like it basically maintain the tight edge, but you have some slack for each edge. Okay, okay. And the way that we're gonna set this parameter is that h here is gonna be something like 8 times d. What is d? D is just the length of this like max flow that you wanna compete with. Okay. So your h is bigger than d. Okay. And the way that okay, how do I define the weight W prime? Here, I just do the same, like I just assign use the same weight from the graph. Okay, like just use the same weight here. But for the backward edge, for each edge, if there is a backward edge in the zero graph, I just use the same weight too. Just a same. This is just simple thing. Okay. In your homework, you will not do this. Yeah. Okay. And the slack, I just make it like so that the slack is like a half factor. Okay. Okay. So now, this is just normal way to initialize weighted push relabel. But now here's a version where it's Relabel-Aggressive. Okay. So what do I do? The idea is like just like push relabel, but I try to relabel as much as I can before I can push. I only try to relabel. If I can relabel, I just relabel. Okay. So there's a main loop that just repeat. Then, as long as there exists an active vertex, okay, the active vertex. Actually, this is called active. Yeah. There is a active. No. Sorry, not. So sorry. This is not active. The active node is just the one that is not dead and it has access. I'm not looking at active node. I'm looking at any node that is not dead yet, and it's like the sink is already saturated. This is what it means, right? The sink is already saturated. If this is more than 0, then it's unsaturated sink. Here I just look at any node that the sink is not dead and the sink is already saturated. And there is nothing that is tight out of it. If there is such a node, it's okay to relabel, to increase the label, because U has nothing tight out of it, so I can relabel it. Okay? So if there exists this guy, I just relabel. just keep relabel as long as I can. Okay. So note that this is similar to when you do approximate shortest path. Decremental shortest path. When you do shortest path, you just keep relabel, play the gravity, right? Relabel, like make the node label as big as possible. This is just what's happening here. Okay? The same thing like shortest path. So this is the point here is just to review shortest path as much as possible. Okay. So until you don't know, you cannot relabel, then come here. What do? Just see if there is an active guy. That is, there is some node that is not dead and has access on it. Okay. So once that happens, then okay. At this point, after this point, right? What you're gonna get is like all the node, such that at level 0, this is the node whose sink is like this is unset sink, right? And then what you're gonna get is like basically kind of shortest path tree. Right? So everyone now is like, everyone here is just gonna have some tight edge out of it. Because like if there is none, then you just relabel. So every node you will have some tight edge out of it. Unless it's dead. If you're not dead, then you have some tight edge out of it. This is what happened after this point. Now just look at, okay, where if there is some node with access, some active guy, maybe the access is here. Access is more than 0. Then we just look at the path from U to the unsaturated sink. Okay, so look at the path along the tight edges. This is the edge that I draw here is just all tight edges. There's going to be the path along the tight edges, along tight edge. The path P in this is tight, all these are tight, okay, to unsaturated sink. Let's call that P. And we're just gonna like augment along this path. So I find this path and then I augment along this path. Right. Once I augment, then I just go to the next round. So this is really like this object that I'm doing actually is not a pre-flow. You see like whenever like I really just always previously I kind of just push one step and access don't reach the sink yet, and then I need to push again. It might not reach the sink, but here I really kind of review the whole path and move from source to sink in one go. So it always a flow, not a pre-flow. Make sense? Okay. So keep doing this. Like once I push the flow, then like the edge is like the edge is flipped in residual graph and continue. Okay. So at the end, if there is no active vertex left, it just means that all nodes with access are dead. All nodes with access have labels H. And then you just return the flow. Okay. So it's the same thing, except that just keep the label as much as you can so that it reveals, like you kind of see the whole tight path and then send the flow along that tight path. Is the algorithm clear? Questions? Okay. Good. So yeah, F is a flow, not not just pre-flow like before. It's always a flow. And the running time of this algorithm is just, you can just say that it's gonna be like dominated by type H data structure, which has something like running time, something like H, and each node you relabel H time, that's why you get NH, and each edge you relabel like each edge you're gonna, for each edge you spend this much time. Actually, it's something like you spend something like this minus the slack. No, actually you spend something like H over the slack, but the slack here we set it to be something like the slack is, one sec. Yeah, but our slack is W, right? It's of order W. What's going on? Yeah, anyway. Yeah, our slack is of order W. So this is running time. Okay. That's the algorithm, and the running time is kind of clear. It's like, basically this is something like D times this thing, which is kind of what we want here. What we want here, you're gonna have some epsilon. You're gonna see how to do it yourself here. But okay. But that's the algorithm, and now I'm just gonna tell you why my flow is near optimum. Yeah.
A question about runtime.
Yeah.
So, like when you trace a path, doesn't that take some time to, like?
Yeah, the time for the to trace the path, you can charge it to the time for pushing.
Oh.
But the time for pushing we have about it before, which is gonna be something like this. Yeah.
So it's like you push as when you trace the path. So.
Yeah. When you trace the path, you're gonna push along that path for sure.
Okay.
Yeah. So charge that to time for pushing. Yeah. Okay. Now I just gonna tell you why this flow is near optimum. Okay. So there are two a big claim about the structure of the flow. Okay. First, it says that the flow is such that it will make excess and unsaturated sink far away in residual graph. So the excess to residual sink to a unsaturated sink, they are far away in residual graph with respect to W. Okay. That's the first thing. This is a thing that already is certified by push relabel, even previous version. Okay, it's gonna be true here too. Now, we will prove this soon. The second structural property is that this flow have small average length. This is a new thing about the Relabel-Aggressive version. This is certified already before. This is certified here in this version. So, okay. We will prove this soon, but suppose that you believe this, then let's see why, like if I set h to be like 8D, then we're gonna prove that the flow is now like a big enough. Okay, so the idea is kind of the same, like how we have done this. So what we do is that we just kind of look at residual graph GF, okay, and I'm just gonna consider the flow. I'm consider the flow F prime, where the flow is doing something weird. It starts by kind of revert the flow that you have found F. It revert the flow, and then it add like F star. Okay, so this is a valid flow in GF, right? Because you can cancel the flow that you have done first and then augment this thing, F star. Okay. And the claim is that if this is not true, if our flow is actually really small, then this F prime actually will have large average length. But that will not be possible because we know that GF in residual graph, like the axis, the source and sink in GF are far away from each other. But this is the flow in GF and it has average length like small. So that's contradiction. That's the plan. Okay. So let's try to prove this. Okay. So F prime is the flow in GF respecting residual source and sink. So it respects this basically like excess function and kind of unsaturated sink. Okay. And we have seen before that, okay, the total weight of F prime when you have F prime is a sum of two flow, the total weight is just at most a sum of the weight of the two flow. Okay. But what's the weight of, maybe I do it for you here. The weight of F star is just going to be at most D times F star because F star by our assumption, it has small average length. At most, it has average length at most D. Okay. So this is at most D F star. What about this? This here, I just use this. Yeah. So the average length of minus F is just like I will show soon that like our flow F has small average length. How small? Something like 2h. So this means that this thing is at most 2h times F. Okay.
Sorry, just to clarify, is negative F like the flow but going backwards? Like, okay.
Yeah, this is the flow that's going backward. But note that like we set the weight here to be the same for both backward and forward edges.
Gotcha.
Yeah. So this is where we use this. Yeah. Okay. Okay, now just calculate. So we have that like h is something like the 8D, so this is less than h over 8. And we assume that f here is small. F here is smaller than like 1 over 16 f star. So you get this thing, okay? And this is just h over 4 f star. But, you know, like f star is like big compared to f prime because f prime have size f star minus f, right? Yeah, the value of f prime is just like f star minus the value of this guy. Okay, so F star, this you get this thing, but oh, actually you even have like, yeah, over 16 here, which is more than half. So this thing is less than h over 2 times f prime. But yeah, so what we get so far is just that the average length of f prime is less than h over 2. So like it means like you can send flow from residual source to the residual sink with average length less than h over 2. But we promise that like every residual source and every residual sink have like distance more than h over 2. So that's contradiction. Okay. So now just from here you get that f must be quite big. Okay. Good. All right. So now let's try to prove this and here. Okay. So the first thing is just the same. Like what are we gonna do? Okay, we're gonna prove this one. What I'm gonna say is like I'm just gonna prove this, that the distance from like access to unset sink is at least h, but in the weight of like a w plus the slack. If this is true, then it implies this thing, because what slack is like w over 2. Okay, so you actually get something like slack is like w over 2. So this is like the weight of 0.5 w. So actually this distance with respect to w in GF actually is something like h over 0.5. Yeah. So it's more than h over 2. But why this is true? Well, it's just the same thing like before. Like we know that all the guy that is not like all unsaturated sink will have level 0. All the excess will have level h. Like the level are far away, but every edge are basically relaxed with some slack, meaning that the level is like at most the distance, but the distance with w on w with some slack here. Okay, so the edges are relaxed, but you allow some slack. Okay, so so combining this thing, you just get this. It's the same thing. Hopefully it's okay. Right. Now next we will prove that the average length of f is at most 2h. How exactly? I'm just gonna prove this. Okay. That the average length of f in terms of w minus slack is at most h. But again, like delta is like w over 2. So it just means like the average length of f in weight with respect to weight w over 2 is at most h. So the average length with respect to the weight w is at most 2h. Here imply this thing, because we set delta to be w over 2. Right. Okay. Do you kind of actually, yeah. Anyone want to say why this should be true? Why it's intuitive? Yeah, what we're gonna need to do is like to see why this is true for the Relabel-Aggressive version, and why this is not true for the previous version.
Is that because like when you were explaining the Relabel-Aggressive version, the way we do the flow is kind of the path, and all the edges along that path are tight?
Good, exactly. Like we literally send the flow along tight path. What's the tight path? Tight paths are like shortest path. Tight paths are literally shortest path, except that we have slack right now. Okay. So like, yeah. So let's see. We know that like we send along tight path. Let's say this is just tight, no slack. Okay. Then we know that like the length of this path here, if it's just tight, this length must be less than h. Okay. Because it's just like it's just the shortest path, such that the length is like this guy is not dead yet. Like the level here is 0, the level of the dead guy is h, and this is like just the distance. Like this guy has some level less than h, and this is like this path is like the length of the distance, which is less than h. Okay. So every path that we kind of send from source to sink have distance less than h for every path. So we keep augmenting flow along path of distance less than h. Okay. So if you keep augmenting flow along path of distance less than h, then the average length of the flow will have like average length less than h too, because average length of the flow is just the average length of each flow path. I'm cheating a bit actually. Let me not cheating, but okay. Let me make it more clear. Okay. So let's consider this path P. The whole path is stretched. It's delta stretched. What does this mean? Let's recall. It just means that for every edge, UV is basically almost stretched, except that you have slack of delta. So it means that if you sum over all this thing, sum over like sum this thing overall, sum over UV in the path, you get that this thing would be like W minus delta of the path, and this thing is just like the level of the first guy and the level of the last guy Z something. This is sink, so this has level 0. This is not dead, so this is less than h. So this is less than h. So it just means that the weight of P with respect to W minus slack is at most h. Okay. So we like just augment along the path of this whose this length is at most h. Okay. So even when we assume that each augmenting path that we augment, even if they never cancel each other, then the average length would be at most h. Now, the path that we augment might cancel each other. When they cancel, it just means that the average length only decrease. So, yeah. So with flow, when the flow path can cancel, like for like the first path you send something and the second path you cancel the first flow a bit, then it would only decrease the average length. So the average length after cancellation is still at most h2. Okay, good. Okay. So This is why this thing is true. Okay. Now I want you to tell me why this is not true in the normal push level. Yeah.
Because we can sometimes send flow partially and then keep stretching out the path after we've sent flow along it.
Very good. Exactly. Yeah. Let me give you one example. Like, imagine that the graph is just the whole graph is a path, and this is S, this is T, and the whole graph is a path. Okay, and in the beginning, everyone is like at level 0. Okay. What I could do is like I put number like U1, U2, U3 up to UN. What I could do is like I just relabel U1 here, and then I push it to U2. Then I relabel U2. U2 is now here, and then I push the access to U3. And I never go beyond level 1 actually. Like I just keep push the next guy, push UI, I relabel UI, push to UI plus 1, and keep doing this. Okay. So the whole path have length n, but the level is just 1. Okay. So H can be really tiny, and yet I can send flow along really like a long path. Okay. So this is not, this kind of guarantee will not be guarantee for the normal push level. Okay. So it seems good here, but at the same time actually it's bad too. In what sense? In the sense that imagine that you want to solve max flow on this graph when the graph is just a path. In the Relabel-Aggressive version, you will actually try to relabel until this guy have level n. When you relabel this guy to level n, it means that like there are something like order n nodes that you relabel for n times. So the total running time is n squared. So it means that this algorithm, even on the graph that is as simple as a path, it spends n squared time. But this algorithm, the normal version, the level is just 1. So the running time actually is like a ON, which is good. Like the path, it should be simple. It should like be easy, and you spend n time. Here you spend n squared time. Okay. So it's like a nice guarantee, but it costs you something. Okay. But anyway, this is where we crucially exploited this version. So So here's a message that you wanna kind of keep in mind. Any version of push label, what it does, like what you remember as an algorithm, what is push label? It's just a way to make excess and unsaturated sync far away. That's all it does. Yeah, it guarantees residual source and sync are far away in residual graph. Yeah. But the Relabel-Aggressive version, it just additionally guarantees that your flow have average short length. And this thing together will imply approximation guarantee, as you just seen. And yeah, in the homework, you're gonna now basically try to make it strengthen this to just 1 minus epsilon. And the hint is that maybe consider the weight function, where like these things are not the same. The weight on original edge is the weight, but the backward one, maybe scale it down. Yeah. The slack is kind of just half of this. Yeah. So you see like in the version without weight, we just set this to be 0. I just set this to be 0, but then the slack would be 0. But our running time is kind of something. Our running time in the weight version, the running times look like sum over edges, h over slack of that edge. But if the slack is 0, then it's not good. So that's kind of why I kind of want this to be small, but I cannot make it too small. Okay. Yes, and you can think what should h be and like how to make it work with capacitor graph, how to use together with link cut tree. This will kind of bring all the things that we have learned together, and you try to solve this. So I hope this should be really good exercise for you. Yeah. Okay. Yeah.
With the link cut tree, you will have the log n approximation factors, right?
You will pay log n in the time,
Yeah.
not in the approximation.
Okay. Yeah.
Yeah. Right. Okay. Yeah, that's kind of why you will get log n here. That's link cut tree. Yeah. Okay.
Are we like? I remember you mentioned we use link cut tree to assume that we can get like the path decomposition of the flow.
Yeah.
Is this a different way to use link? Like, are we using link cut tree to do this or do something else?
No. Like so. It's something else.
Okay.
We try to use link cut tree here so that we don't push. We try to push along like long path. Like so you see like here when I push along this path here, like if it's saturating, okay. If you remember, like the time for saturating push is going to be small, and but the time for unsaturating push can be big. The point of using link cut tree is to kind of just you kind of make it such that every push is basically saturating by like kind of look along the whole path and see like which one is the which one is smallest and then push so that like some guy is saturating. Yeah. Okay. So try to think like it's gonna be like, but okay, but I mentioned again that like a link cut tree can be used to route the flow to be integral. That's kind of different application. Yeah. Okay, good. So this will be in your homework. I will post it like today. Yeah. And let me discuss quickly about what we left off last time, that we cheated, right? So we said that like our algorithm for n square max flow first just compute a hierarchy and then build a shortcut graph and then run this short flow algorithm that we just seen on the shortcut graph and then project it down to project the flow down to the graph. Okay. And then scale it a bit. So this is the two places that we cheated. We actually don't know how to build a hierarchy fast yet. And we don't know how to, we didn't say how to project it down algorithmically. We just know that this flow, there exists a flow that you can project down. Okay. Okay. So first, let me so next class is gonna be about how to build the hierarchy fast. Okay. The way that we're gonna show is just gonna be a new way, actually, new way to build hierarchy. SE hierarchy we learn how to build it fast already. It's top down. If you remember, we find expanding balance separator and recurse. That's the way that we learn how to build SE hierarchy. Now we're gonna, and basically, you can hope to build it top down this way in the related graph too. Okay, so in several lectures ago, we learned how to build this SE hierarchy in an unrelated graph using Polylog MacFlow using card matching game, and we do it top down. Okay. We can generalize this. I claim we can generalize this to the related graph. Generalize this algorithm with Polylog MacFlow to the related graph. It will actually give you close to linear time algorithm. By the way, this is just my claim. This thing is not explicit in literature yet, and it might be a kind of nice project. Anyway, we don't do this, but yeah, it's a nice thing to try to make it formal. But I really strongly believe we can do it. But this will give you this running time, but we're gonna do it without black box MacFlow. And we're gonna do it bottom up. You're gonna see how, yeah. But the way that we're gonna do is actually, we need to relax the notion of SE hierarchy a bit. And once you relax that a bit, you can do it bottom up in a much simpler way, which is just do expanded decomposition bottom up, but not like recurse and contract. We have seen a bottom up approach that we recurse and contract. That version, if you remember, it gives you 3 flow specifier. You find boundary link expanded decomposition and find that, and for each component you contract, and you get smaller graph and repeat. That version you will need to pay n to little 1. Here we don't want to pay n to little 1. We can get polylog. Okay. So next time we see this. Okay. And for fast projection, well, okay. Do I want to discuss this? Let's see. Let me discuss this, yeah. Actually, maybe no. Okay, you can have a look, but if I have time, I would still try to this is just some discussion. How can you hope to do it? Yeah. But we're gonna do it formally anyway. So yeah. Okay. Any questions?